Hi friends, we are still in chapter 4 and we are looking at linear functions and relations. We're going to talk about scatter plots and lines of best fit. You guys are familiar with scatter plots. You remember that we had these last year. We talked about them. Scatter plots deal with two variables coming together as a data point. So I can talk about the height of a person and how many smiles they got that day. And I could relate those two and put it as a dot. Some data points are going to just kind of be blobular, just a blob of stuff that doesn't really show a trend, really, is what I'm trying to say. And we would say that a data point in that situation has what we would call no correlation. So this first example is no correlation. If you guys are remembering correctly from last year, you would remember that when we see something moving, as one variable increases, the other one increases. If that's the general trend, we call that a positive correlation. And I'm sure you can guess it even if you don't remember what the next situation is going to be. This is a negative correlation. And we see that it kind of relates to the slope of a line, right? When we have a positive slope, it goes up to the right. When we have a negative slope, it goes up to the left or down to the right. And so that's what we'll be discussing today, and the relation with scatter plots with lines. Let's take a look at some vocabulary. Our vocabulary today has 4 terms. The first term is bivariate data. It's data, not date. Sorry about that. It's data with 2 variables. So basically, anytime you're comparing 2 things, height, weight, X's and Y's, that's called bivariate. You've got two pieces of information that you're working on. Okay, scatter plot is a graph of data with 2 variables on a coordinate plane. And you guys are familiar with that. A line of fit is also referred as the trend line. And this is the perceived line that data on a scatter plot may fall close to. And we'll look more at that. This is kind of the new piece that we're adding this year as opposed to last year. And then finally, linear interpolation. It's using the line of best fit to predict values within the boundaries of the data range. So you've also done this as well. You've done this in the 6th grade, if not last year, where we will find an equation of a line and use that information to find other information that's not expressly given to us in the data. All right, so the first example we have, example 1, we're going to evaluate a correlation. This is pretty straightforward. Unfortunately, I feel like this might be so tiny. So I'm going to have to make this a little bit larger. This x-axis, or the horizontal axis, refers to the weight in pounds, and it goes up to, I think it starts at 10 and it goes up to 50. And then this vertical axis refers to height in inches, and we've got 10 here and up to 40 here, just to give you guys a sense of what's going on. Honestly, you really didn't need that to determine whether this is a positive or negative correlation. The first part of the answer is that this is certainly a positive correlation, right? And you guys can see that just because it's as one increases, the other increases. So that's a positive correlation. And with that in mind, the next thing we need to do is describe what the situation means. So I told you that this was weight and this part is height. It's kind of hard for me to write this down. Height. I guess that's good. Height in inches. Maybe they're talking about a small child. Maybe they're talking about an animal. I don't know. But, you know, we're going up to 50 pounds. We're going up to 40 inches. And so what we can see from this is that as the weight increases, as the weight increases, the height increases, or vice versa. As the height increases, the weight increases. So that's how we would explain the situation. Not a big deal, stuff you've seen before. So that's all that will be expected of you in a problem like this. But the problems do get a little bit more challenging. As you see here in example 2, we're going to write a line of fit. And so the first thing that we need to do here, we have, and I didn't explain this data because it was just like a lot of information, but basically the situation is as follows. Somebody's measuring the vertical drop of roller coasters since the year 1998. So 1988, pardon me. So we've got 1 year since 1998, 3 years, you guys get the idea. So you would add the one onto that and add 15 onto that to actually figure out the year. The vertical drop is given in feet here, and we see that it looks like just by glancing that we have an increase in the vertical drop of roller coasters. So the first thing you want to do when you want to write a line of fit is you want to draw it in. So what we need to do is plot the points on our axis. We need to create an X and Y axis, or since 1988 axis and vertical drop axis, and we're going to graph the points. Let's do that first. First thing I needed to take my time and label each axis. So here I have years since 1988, and I counted, I skipped a space and counted by 2, so I was consistent across the horizontal axis, and then the vertical axis, I started at 0 and I'm going up by hundreds. And what I do is I check to make sure that does that contain the data information that I have here. It's going to be a little bit of a challenge to graph, but we'll be okay. And so the next thing we're going to do is plot the points painstakingly. We're going to do that, and so you'll see the points displayed in a moment. Okay, so we did it. Not super clear as I'd like it to be, but it's good enough. You can see all the points are plotted, and I think that you guys can check out the fact that we have a positive trend here, right? It's going up. And so when you draw a line of best fit, if I had like a spaghetti, if I had a piece of spaghetti, a piece of hard spaghetti, I would lay it down and kind of show you how your line could lay. So what you do is I'm going to take this highlighter and you kind of approximate where the line would be. And when I'm talking about the spaghetti, I'd kind of be adjusting it side by side, or using the two ends to adjust it and see where the line of best fit is. So I'd try to figure out where I could find it so that the data would fall, all the data would fall as equally distant to my line as possible. And it really is a little bit of finagling, right? You're going to have to finagle it. It's not going to be perfect, and everybody's equation for the line of best fit won't be exactly the same. So once you figure out where you're going to, put your solid, your dry spaghetti, right? Where you figure out where you're going to do that, you're going to draw a line. I'm going to try to draw a line as neatly as possible. I know this is never an exact science here with me and using this technology. The technology is difficult, children. Let's see. We're going to try. That's not the line that I want. We're going to try again. This time we're going to use a pen. I promise it'll be okay. All right. Let's say right here. Let's say I say this is my line of best fit. That's pretty all right. You draw your line of best fit, and then you choose 2 points. Now we got to come up with the equation of it. We did it, woohoo! Now we got to choose 2 points from the data that we're going to use. So the point that I'm choosing is this one, 155. And then the other point that I've chosen that I've passed through, it looks like 12. It looks like the bottom one, so 12,300. 12,300. And so you guys got it. After all of that work, we're going to have to do what we've been doing in the past couple of sections for a long time. We're going to find the equation of a line. Do you remember the rules? First thing you need to do is find the slope. And then you can use, I don't know, whatever you want to use, but I think I'm going to use point slope. So y minus y sub 1 is equal to m times x minus x sub 1, and that's how I'm going to find my equation. So when I find the slope, I've got to do change in y over change in x, 300 minus 155, and I'll spare you guys the details because I know you can do it. So I got my slope, plugged it in here, chose a point that I found convenient. I just like the 300 as opposed to the 155 in this ordered pair, so I chose this one, y minus 300 equals 145 times x minus 12. Let's go ahead and put it in slope-intercept form. So we would end up with this. I think I had 145. I put 145 down and not 145 over 9, which is the actual slope. My bad. And then I distribute through, go ahead and do my thing, and this is what I end up with as an equation. Not cute, but okay. And when we get equations like this, the cool thing is now if somebody said, well, what do you think the vertical drop of a roller coaster would have been in 4 years after 1988, and we don't have data for that, we can use our equation to kind of predict that. And that's what we're going to talk about in this next example. This next example is example 3, our final example. I know you're clapping. Use interpolation or extrapolation. Use the scatter plot to find the approximate test score of a person who studied 15 hours. So this is right up our alley. If you notice, 15 hours of study has no correlated test score. So apparently anybody who was in this study or who reported this information, that nobody studied 15 hours. They studied other hours that are indicated here. So what we would do with this is, again, we would try to find the line of best fit, and I'm going to spare you guys my chatter, and I'm going to find the line of best fit. Be right back. So I zoomed in a little bit. As we said before, this is not an exact science, but what I'm looking at here are the two data points that I feel like I'm close to, and those data points look to me to be 762. So 7 hours of study got us 62 for one student. And then this one over here, this looks like about 20, I'm going to go with 23 hours, and that looks like an 88 to me. So 23 and an 88. So I'm going to do exactly as I did last time. I'm going to use these 2 points to come up with an equation. First thing I'm going to do is find the slope. Next thing I'm going to do is use the slope, point slope, sorry about that. And then after I do point slope, look at me getting it wrong. After I do point slope, I'm going to change it into slope intercept. And I think that'll be it for our example. So let me do the slope. So notice I've got my slope. I did change in y over change in x. Next, I'm going to put it in equation form. I chose to use this ordered pair, and here's our equation. And finally, in slope-intercept form, here's what we got. And so we end up with this. And the reason why we did all of this is because, remember, we wanted to calculate how well a student would have gotten given this data information if they studied for 15 hours. So now I'm going to put 15 into my equation and solve. Y is equal to 13 over 8 times 15 plus 405 over 8. I know you're using a calculator, so am I. Let's go ahead and figure out the rest of this. And I have y is equal to 75. So if you study for 15 hours for this particular test, you would get 75. All right. With that in mind, my friends, we saw that, and let me just talk about this really quick. The title was interpolation versus extrapolation. Interpolation is related to extrapolation. Interpolation means, figuring out, predicting information within, and extrapolation means you're extrapolating, you're going kind of outside the boundaries of what you've been given and figuring out if you can extrapolate some concept. So we interpolated by creating the line given the information we had, and we used that to extrapolate the information about 15 hours of study. All right, let me get this back to a normal size. Oh, you can see everything here. Here's your assignment. Make sure you do it. Try it as best you can. Let me know if you have any trouble. I can't wait to see you tomorrow. Please do your best, and I'll be talking to you soon. Bye-bye, guys.